The universe is teeming with mysteries. Black holes warp space and time. Among the most intriguing enigmas are neutrinos, often called ghost particles. These subatomic particles are incredibly abundant, yet shrouded in mystery. They possess no electrical charge and almost no mass, traveling at nearly the speed of light. Trillions pass through our bodies every second, leaving no trace. Despite their abundance, neutrinos are incredibly difficult to detect. Their ghostly nature makes them fascinating and frustrating to study. Neutrinos are active participants in the universe's grand symphony of creation and destruction. Their origins lie in the fiery hearts of stars where nuclear fusion reigns supreme. Hydrogen atoms fuse to form helium, releasing tremendous energy. This energy is carried away by light, heat, and a torrent of neutrinos. Supernovae, the explosive deaths of massive stars, are another prolific source of neutrinos. When a star's core collapses, it triggers a runaway nuclear reaction. This cataclysmic event generates a burst of neutrinos that can outshine an entire galaxy. Studying neutrinos provides us with a powerful tool to probe the universe's inner workings. Neutrinos are the ultimate cosmic phantoms, their ethereal nature making them both fascinating and frustrating to study. Their defining characteristic is their weak interaction with matter. Unlike other particles such as electrons and protons, which readily interact with their surroundings, neutrinos can pass through vast amounts of matter from planets to stars without leaving a trace. This remarkable ability stems from the fact that neutrinos only interact via the weak nuclear force and gravity, two of the four fundamental forces in the universe. The weak force is incredibly short-ranged, meaning that neutrinos need to come extremely close to other particles to interact with them. Gravity, while universal, is incredibly weak at the subatomic level, making it negligible in most neutrino interactions. To put their elusiveness into perspective, a neutrino could pass through a light year of lead, a distance of over 5 trillion miles without a single collision. This makes detecting them a monumental challenge requiring incredibly sensitive instruments and massive detectors to capture even a handful of these elusive particles. Their ghostly nature, while challenging, also makes neutrinos incredibly valuable messengers from the cosmos. Unlike light, which can be absorbed or scattered by dust and gas, neutrinos travel unimpeded from the most distant reaches of the universe, carrying with them valuable information about their origins and the environments they traversed. Detecting neutrinos is a monumental task, akin to searching for a single grain of sand in the vastness of the Sahara Desert. Their weak interaction with matter means that they pass through most detectors without leaving a trace, requiring scientists to develop ingenious methods to capture these elusive particles. Neutrino detectors are often built deep underground or underwater to shield them from cosmic rays and other background radiation that could mimic neutrino signals. These massive detectors, some as large as office buildings, are filled with thousands of tons of ultra-pure water or other materials, creating a dense target for neutrinos to interact with. When a neutrino does interact with an atom within the detector, it can produce charged particles, such as muons or electrons, which travel faster than the speed of light in the detector medium, creating a cone of light known as Cherenkov radiation. This faint blue light is captured by sensitive photomultiplier tubes lining the detector walls, providing evidence of the neutrino's passage. However, even with these sophisticated detectors, capturing neutrinos remains a rare event. Only a tiny fraction of the trillions of neutrinos passing through the Earth each second will interact with a detector, making neutrino experiments exercises in patience and precision. Despite the challenges, the insights gained from studying these elusive particles make the effort well worth it. In the 1960s, scientists embarked on an ambitious quest to measure the flux of neutrinos streaming from the Sun. Solar neutrinos are produced in the nuclear fusion reactions that power our star, and their detection offered a direct way to probe the Sun's core and confirm our understanding of stellar evolution. However, the initial experiments yielded a perplexing result. Only about 1/3 of the expected neutrinos were being detected. This discrepancy, known as the solar neutrino problem, sent shockwaves through the scientific community. Had our models of the Sun been wrong all along? Were there unknown particles or forces at play? The mystery deepened as subsequent experiments using different detection methods and located in different parts of the world confirmed the deficit of solar neutrinos. The solar neutrino problem remained one of the most enduring puzzles in particle physics and astrophysics for over 3 decades. It challenged our understanding of both the sun and the fundamental nature of neutrinos themselves, leading to a flurry of theoretical proposals and experimental efforts to resolve the discrepancy. The solution to the solar neutrino problem came from a surprising source, the realm of quantum mechanics. It turned out that neutrinos, those elusive particles that rarely interact with anything, were not as straightforward as they seemed. They possessed a hidden talent, a quantum quirk known as neutrino oscillation. Neutrino oscillation, first proposed in the 1950s but not experimentally confirmed until decades later, states that neutrinos can change their flavor as they travel through space. Just as a chameleon changes its color to blend in with its surroundings, neutrinos can oscillate between three different types, or flavors: electron neutrinos, muon neutrinos, and tau neutrinos. The implications of neutrino oscillation for the solar neutrino problem were profound. The early experiments, designed to detect only electron neutrinos, were only capturing a fraction of the total solar neutrino flux. The missing neutrinos were not gone. They had simply transformed into muon or tau neutrinos, which the detectors were not sensitive to. The discovery of neutrino oscillation not only solved the solar neutrino problem, but also revolutionized our understanding of these ghostly particles. It demonstrated that neutrinos have a non-zero mass, a property not predicted by the standard model of particle physics, and opened up new avenues of research into the fundamental nature of matter and the universe itself. The standard model of particle physics, a remarkably successful theory that describes the fundamental particles and forces that govern our universe, had one glaring omission. It predicted that neutrinos should be massless. However, the discovery of neutrino oscillation threw a wrench into this neat picture, revealing a crack in our understanding of the subatomic world. Neutrino oscillation implies that neutrinos must have a non-zero mass, albeit incredibly small, perhaps millions of times lighter than an electron, the next lightest particle. This discovery has profound implications for our understanding of the universe, as it challenges the completeness of the standard model and hints at the existence of new physics beyond our current understanding. The exact masses of the three neutrino flavors remain unknown, but their non-zero nature has opened up a Pandora's box of questions. What gives neutrinos their mass? Are there other, heavier neutrinos yet to be discovered? How do neutrino masses affect the evolution of the universe and the formation of galaxies? The discovery that neutrinos have mass has ignited a new era of research in particle physics and astrophysics. Scientists are now racing to determine the absolute masses of neutrinos, understand the mechanism that generates their mass, and explore the implications for cosmology and our understanding of the universe's evolution. Neutrinos, once thought to be insignificant bystanders in the cosmic drama, are now recognized as playing a crucial role in shaping the universe as we know it. Their influence can be traced back to the very early universe, just moments after the Big Bang, when they were as abundant as photons, the particles of light. As the universe expanded and cooled, neutrinos played a crucial role in the formation of the first atoms. Their interactions with protons and neutrons helped to set the ratio of hydrogen to helium in the universe, a fundamental parameter that governs the evolution of stars and galaxies. Furthermore, neutrinos' slight but non-zero mass means that they contribute to the overall mass-energy budget of the universe, influencing the expansion rate of the cosmos and the formation of large-scale structures such as galaxy clusters and superclusters. Some scientists even speculate that neutrinos could be a form of dark matter, the mysterious substance that makes up the majority of the universe's mass. Understanding the role of neutrinos in the early universe and their influence on the evolution of cosmic structures is a major area of ongoing research. By studying these ghostly particles, we can gain valuable insights into the fundamental processes that shape the universe we observe today. Neutrino research is a vibrant and rapidly evolving field, pushing the boundaries of our understanding of these elusive particles and their role in the cosmos. The future of neutrino research promises to be even more exciting, with several major experiments and theoretical efforts underway. One major focus is to determine the absolute masses of the three neutrino flavors. Several experiments around the world are racing to make this measurement. Another goal is to determine whether neutrinos are their own antiparticles, known as Majorana nature. This could provide clues about the processes in the early universe. Neutrino astronomy, the study of neutrinos from astrophysical sources, is rapidly growing. By detecting and analyzing these cosmic neutrinos, we gain unique insights into the universe's most energetic phenomena. The study of neutrinos offers glimpses into the fundamental forces and particles that govern our universe.